Hello everybody. So, today's lecture is going to be on section 12, known as wiring methods. And there's quite a few wiring methods, to say the least. This is going to be part 1 of section 12. If you remember from, I believe in the intro to code lecture, but all the same, if you remember, I mentioned it at one point that section 12 is the largest section of the codebook. It might be sort of obvious based on its title, wiring methods. Wiring method, an example of a wiring method, let's just speak generally, because this is a general section of the codebook. A wiring method might be EMT, electrical metallic tubing installed surface mounted on masonry in a commercial building, and then you pull conductors into the EMT, and the EMT has boxes and it comes from the panel, and it's this whole interlocked network of tubing. Another method could be USB cable run from the transformer on the pole underground and then up through PVC to a meter for a house service. And we talked about services in a previous lecture. Another wiring method might be NMD 90, or non-metallic sheathed cable, or sometimes called Lumex, which is the brand name, or one of the brand names. It might also be called Romex or Rumex, I can't remember the other one. But those are examples of wiring methods, and how we get electricity to where it needs to be from where it comes from is basically a wiring method. So there are a lot of options, and there are a lot of ways to satisfy all kinds of conditions. And so let's start looking at wiring methods. And, wiring methods also answers a big existential question of, why are we here? We're here to wire some things. Okay, let's get serious. So, right off the bat, the scope lays out, and you'll see I wrote boss for all these, and also for subrule 2. So the scope of wiring methods is very general, which means if there's another section of the codebook talking about class 2 circuits and the wiring methods needed for class 2 circuits, you follow that section of the codebook. Same thing for, we have section 54, community antenna and radio and television, cool optical fiber cables are going to have their own wiring methods, so on and so forth. So wiring methods is a general part of the codebook. 12010 talks about wiring in ducts and plenum chambers. So, in general, we can't just run cables in ductwork. That's just kind of a general thing that you may learn throughout the trade. But there are maybe times when we can run them. For example, number 5, and this one might have come up, or it might make sense if you've done residential. Because number 12010 subrule 5 says where a furnace cold air return duct is formed by boxing in between joists, wiring methods specified in this section for use in the particular location shall be in accordance with, and we'll go look at these 2 rules in a minute. And so what that means is, if instead of ductwork, instead of metal, sheet metal formed usually in a box or in a circle for moving air, if instead you just kind of make a box between 2x4s and use that as your return air, then you might be able to run wiring methods in that boxed in return air. Now, duct might make sense if you're not sure what a duct or ductwork is, and you can go to the furnace where you live. That shiny silver metal stuff going to and from, or it might look like they're just both going to the furnace. That shiny metal, sheet metal, that's ductwork. And all ductwork, at least for HVAC equipment, basically all ductwork is a plenum, but not all plenums are ductwork, such as Subrule 5. So, what is a plenum is answered in section 0. So here we are, section 0. Awesome section. This is our dictionary. We don't need, get out of here Oxford, get out of here Merriam-Webster or Collins, I don't know, all the dictionaries. Because I got section 0. I don't need dictionaries anymore. I mean, I still do, but plenum in section 0 is defined as a chamber associated with air handling apparatus for distributing the processed air from the apparatus. A furnace might be one of those apparatus or apparati or whatever. Processed air from the apparatus, supply plenum, to the supply ducts, or for receiving air to be processed by the apparatus, return plenum. So that's the definition for plenum. So when you box in the joists, or when somebody boxes in those joists, that makes it into a plenum. But it's not ductwork, but it functions in a similar manner. Now, another example of a plenum is when we install, or not us, but when somebody installs a dropped ceiling or a T-bar ceiling where you just place in the tiles, and you have, apparatus or air handlers or rooftop units or whatever supplying air into that space, and they also usually have a return air to some degree. Sometimes what will happen is you'll see a little grill that's just open to the ceiling space, open to the space above the T-bar. And that grill is a return air grill because the HVAC equipment pumps in tempered air, heated or cooled or whatever it's supposed to do. And as that air fills the room, some of it will go up into the ceiling space, up through that return grill. And so we would call that ceiling space a plenum. Now, ultimately, whether or not it's a plenum, even if you logically can argue that it's a plenum, if the inspector says it's not a plenum, then it's not a plenum. That's sort of ultimately how it works. And so if you're going to put cables in a plenum, they have to meet 2130 and 2132. And basically the reason for that is if we install wires in a plenum and a fire starts in that plenum, we don't want our cables and wires to act like a candle wick, essentially. We don't want the fire to travel down the wires, and then they would melt the wires, and the wires would spark and cause more fire, etc. I just said etc. weird, but anyway. So we don't want our wires to cause more fire. So if we're going to put them in a plenum, they have to prevent flame spread or fire spread, right? And the same thing for non-metallic raceways. So we're going to jump over to Appendix B, just to clarify all this plenum and fire prevention stuff. So Appendix B, 2130, I'm on page 546. So if you've ever seen data wires or control wires just kind of run free air, tie wrapped to whatever in a ceiling space above the T-bar, that wire should be, and it hopefully is, FT6 rated. And it'll say it right on the cable. And the reason it has to be FT6, if it's in that T-bar space, and basically run as a free-aired multi-conductor cable, is because spaces between a ceiling and floor or ceiling and roof that may be used as a plenum in buildings in buildings of combustible or non-combustible construction must be FT6 rated. The jacket has to be FT6. FT1 such as NMD90 or Lumex that you might be installing in a residential house, is just for combustible construction. So that's why you can only run it in that boxed in joist space that we talked about at first, because that Lumex is FT1 rated and it's in a plenum. So it has to meet that rating to prevent the spread of fire. So that may have seemed like some information that was not electrical or codebook specific, but I wanted to explain plenums and stuff in case people had not come across or worked with much HVAC equipment. Next rule, 12012, underground installations. And we already kind of looked at this one when we were talking about services and service requirements, because some of our services are run underground. But not all underground installations are services. We can run underground installations for other purposes. Maybe we got to get across the other side of a warehouse and the ceiling is really, 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 really tall and we don't want to go up there. So before they pour the concrete floor, if that's what they go with, which is usually the case, we might run a raceway down from a panel through the earth, underground, and over to where this big load is. And might be an easier way or a better way to get conductors across this warehouse. Now, sometimes you'll get weird questions such as what size of sand? And you'll look through the code book and say, I don't know, why do I care about the size of sand used in an underground installation? But if you get odd questions like that, you may give a weird answer that suffices, or an answer that is correct. For example, in Appendix B, 120124, the maximum size of sand is based on standard sieve sizes detailed in... Okay, cool. If someone's asking me what size of sand, I say that's my size. Now, that's not a specific size, but that's what the code book tells me. So if I need to go find it, whatever the heck that is, that's where it is. So that's where my sand size is. Now, while we're here, let's look at 12012, subrule 12. And I know we didn't read that yet in this lecture, but the intent of this subrule is to avoid damage to the installation during movement of the building, raceway, or cable. So the building's moving, what might it be damaging, and why is the appendix being specific? So, back to section 12012, subrule 12, where underground raceways or cables are subject to movement by settlement or frost, provision shall be made for the prevention of damage to the conductors, conductor insulation, or the electrical equipment. It also talks about, in subrule 5, where they rise and they go up into a conduit. They shall enter the conduit from a vertical position. So when you run USB cable, for example, if you're running USB cable as a service to a house and you run it underground, you're going to come up through what I always saw was PVC, but you could do some different conduit. But you would run it up through PVC, so it's protected when it gets above the earth. And your module has a fantastic picture that touches on all kinds of other ideas too for an underground installation. But just to say what we're talking about with subrule 5 and subrule 12, this slack right here helps in case, let's say for example, the ground settles and everything goes down and it pulls this cable down. Well, we got some slack here, so it's not going to rip the cable out of the terminations, probably at the meter if this was a service, or at whatever termination point is above here. This slack also kind of, to me, functions as meeting that vertical requirement, because we have this little loop and we come up. instead of having a loop that goes back and then comes back and then goes up, a little slack straight down helps to satisfy both of those requirements of subrule 5 and subrule 12. So we move on through section 12, this gigantic section. Conductors and hoistways. So a hoistway, for example, could be an elevator, a dumbwaiter, something like that. Lightning down conductors, lightning rods, or a conductor used as a lightning rod, sure. Entry of raceways and cables into buildings. So in general, if you've ever had to take take a caulking gun with some kind of red silicone type goo and seal up a hole that you made in a building, that might have been satisfying this, because in general, if we make a hole, we have to fill a hole. Now 12020 is, I mean, it's probably applying to a pretty specific situation. Not that it has to be, we're in a general section, but wiring under raised floors for data processing and similar systems, to me, would be a server room with a subfloor. And so what they often do is they basically, if you can think of T-bar that has tiles you can lift and move, a subfloor has the same thing, but instead it's floor tiles instead of ceiling tiles, and you pull up those floor tiles, and you might put a server rack over top of that floor tile, and then you're going to run cables and wiring in a certain way that satisfies the code book. Maybe the way you run those wires and cables are in this part of the section of the code book. It talks about the raised floor if it's of a non-combustible and if of a conductive material is bonded. So often they will use these little metal legs to hold up the floor. Now, let's put it like this. Let's say this is a little metal leg, and then they'll put the floor on top of it, and each leg will cover a corner of a tile. But that metal leg is going to have electrical wires. Most likely it'll have electrical wires run all around it and through it and beside it. So you may have to bond those legs based on section 10. Now we got 12022, cables or raceways installed in roof decking systems. And we're going to jump to Appendix B because it's going to somewhat explain you cannot install it concealed unless you say that it's concealed, and you can't just put any kind of wiring methods on a roof decking system. You might have also heard it called Q-deck. So let's jump to Appendix B. So here's 12022 in Appendix B. And this is what it's talking about, is you can't conceal it. You can't hide our cables or raceways. Because if someone came and put a conduit or a raceway or a cable or whatever, and they went to install it like this one is, which is an okay way to install it, and they put a screw through here, they might hit this and damage it. Or if something happens to this cable or raceway or conduit or whatever, then you can't really get to that once the roof is finished being constructed. Now, I also put this in here just to remind everybody, when you are installing this way and you have it, on the lower face or on this upper face, both can work. Do not screw up like this, because you might penetrate the roof membrane. Instead, you're going to screw into the side here, or you're going to bend a strap. If this is, a raceway, you're going to bend a strap and screw it up, onto this face. So that's just kind of a don't make the roof leak with your screws PSA portion of the lecture. So now we're on to conductors as a wiring method. Okay, cool. 12100 is maybe obvious, but the code book doesn't deal with obvious or common sense or whatever. Code is code. At least that's how the code book sees it, I think. Code book doesn't really talk to me. I mean, I don't think it should. But anyway, 12100 is basically, sub-rule 1 is saying, if you're going to put a conductor somewhere, it has to be good for what it's going to come across. So if it's, going to be subject to mechanical protection or damage, then it has to be good for the degree of mechanical protection that is going to keep that conductor safe. 12102 is talking about our installation of insulated conductors and cables versus the types of insulated conductors and cables. And so our installation, we can't damage it on purpose or do things that would damage the conductor, such as if the ambient temperature is liable to become low enough to damage the insulation during flexing or movement. We have to be conscious of that and try to avoid that. It has this very specific thing about T90 nylon, which is normally a 90 degree rated insulation. But if you get oil on it, it's 60 degrees Celsius. So that's just kind of a very specific thing. And it also sends us to table 19 for conditions of use. So let's jump there. So here's table 19 on page 483. And we have types of CSA type designations, such as R90, RW90. It gave us conductor temperatures or insulation temperatures, whatever you want to think of it as. That's cool. And then it has all these conditions of use. Now, if you remember table 11 was talking about flexible cables and their conditions of use. So this is for regular conductors, if you want to think of it that way, or these conductors is another way to think of it. And table 19 carries on to the next side. It's got our NMD90, which is a non-metallic sheathed cable. So if you're not familiar with some of these designations, maybe table 19 can help you with all of its, has loads of information, such as a cable not having a metal armor or metal sheath, USEB 90. So if you're wondering if that counts when you're doing an underground installation, how far you can bury USEB, and you're not sure if it has an armor or not, well, table 19 says that CSA designation does not. So table 19 could be useful for that as well. We're also going to come back here in a little bit to look at NS75 and NS90, which are our neutral supported cables. But for now, let's go back to section 12. So here we are back in 12108, talking about conductors in parallel. And so what we can do sometimes, if we have a very large amount of ampacity that we have to get somewhere, and we don't want such huge conductors, we can cut that ampacity in half, or even in a third or a quarter, and run conductors in parallel. Now, there's other factors to accommodate for when that comes in, such as, does the equipment have the ability to have parallel conductors terminated? If not, maybe we have to tap off in a splitter. Do we want multiple breakers? So those are some considerations, but nonetheless, when we run conductors in parallel, there are very specific rules. And we're not talking about having, two 14 gauge wires to feed your dryer, for example, because right off the bat, it says number 1/0 and larger shall be permitted to be installed in parallel sets. So you can think of it as a minimum size for parallel conductors. And if they are in parallel, they have to meet all of these requirements, because any difference in the parallel conductors, such as if one has a splice, or if they're a different size, different insulation, that might change the allowable ampacity of one of those conductors. And if we're running them in parallel, we want them to share the load equally. So if they're of a different length, they might have a different line loss, which is going to start to throw all kinds of things out of whack. If you remember from Edison 3-wire, when we start to have different resistances on wires, we start to get weird voltages, and our equipment and our loads don't really like different and weird voltages. They want some consistency. They want what they're rated for. They don't want weird stuff happening. And when a conductor is run farther from its source, or when it's just a longer wire, it's going to have more resistance. So when they're not the same length, they're going to have different resistances. Now, this is the same length. So if you're asking in code class, yeah, but what if they're pretty close? No, they have to be the same length, exactly the same. Now in the field, pretty much the same is probably going to be acceptable by the inspection department or the authority having an inspection, whatever they want to call themselves. But according to the code book, they have to be the same length. Now, I said up here, they have to be 1/0 to be run in parallel, except, as the code book likes to do, the code book will tell you, yeah, it has to be this, but also, you can be smaller than the 1/0 if it's to supply control power to indicating instruments and devices. So, okay, these very specific situations, you can have something smaller than the 1/0 run in parallel. This 4006 is that temperature rating. If you remember from the section 4 lecture, hopefully you do. So if you're going to splice these parallel conductors, the splices probably have to be the same temperature rating, and they also have to be spliced in the same manner. And if everything has to be the same length, and you're going to splice one wire, you have to splice every single one basically at the exact same spot in terms of length along the conductor. So probably just don't splice it would be the ideal way if you're going to run conductors in parallel. And speaking of splices, 12.112, conductor joints and splices, which is telling us that conductors shall be spliced or joined with splicing devices, or by brazing, welding, or soldering with a fusible metal or alloy. And if you solder it, you have to join them first. So you basically have to splice them and then solder them. Now, a splicing device may be, for example, a wire nut, also known as, much more commonly, also known as a Moret. And a Moret is a brand name. So Morets, those little things those little plastic caps you twist on after you splice your wires together. A Moret is a wire nut, and it's a splicing device. You twist your wires together, and you put a Moret on top, and that Moret is going to function as your splicing device. Now in 12.118, we have termination and splicing of aluminum conductors. Very specific. So copper, you get, some Morets, and you just shove your hand in a bucket of Morets from the work van or from the shop, and you just throw them in your pocket, whatever, and you're just splicing copper all day. But codebook says, whoa, if those are aluminum, you better be careful. You better do it a very specific way. If you've ever done, back to that example I've been talking about for 2 lectures now, a USB run underground or whatever, and you're running, you should run it underground. It has to be run underground for the most part. But you're running USB underground, and it goes up to the meter, and then from the meter it goes to the panel. when you terminate the aluminum conductors, those two live aluminum conductors of your USB, you probably, hopefully, who's ever, helping you or directing you or supervising you, should have gave you a little tube of penetrox, or maybe people incorrectly called it penny chalks. Maybe I called it that for the first couple months of my apprenticeship. Anyway, that penetrox prevents the penetrating oxide film that happens when we install aluminum conductors. And basically when we expose the aluminum under the insulation to the air, the aluminum starts to oxidize and it causes all sorts of problems. Your module goes into the specifics and the science of it. But basically what we want to prevent that. So there's all these specific rules. There's this specific type of compression device that keeps the cold flow, it's called, from basically letting the aluminum move away from the termination or move away from the lug. Because when we terminate that aluminum conductor, we want it to stay. But the aluminum says, nah, I want to get out of here. I'm oxidizing. I want to leave. So we use penetrox and we use these specific types of connectors. If you've ever connected aluminum and copper wires together in a splice, hopefully, and you should have used a specific type of wire nut or splicing device, because the aluminum will basically just wiggle away from that splice. It also has very specific ways of terminating it when there's a binding screw. So most switches and receptacles have a binding screw. It's those screws that are on the side of the device. And so this is saying, you have to basically, the way that screw turns needs to be, so the way the screw turns, if you're turning it clockwise, the loop of your aluminum wire has to go the same way. So as you tighten the screw, it grabs that wire and tightens it more. So that's what sub-rule 6 is talking about. And this is just for aluminum. So aluminum's nice because of how affordable it is, but there are specific rules. So if you're just dealing with the problems of terminating aluminum conductors when you do the service, that's not too bad. But if you're doing it throughout a whole house, maybe that's a pain. Maybe that's not worth the savings you get. And if you're wondering about the difference between copper and aluminum, aluminum's also going to be bigger. So for almost the same ampacity, aluminum will always be one size larger than copper. So it's going to take up more space as well. So what a 14 gauge copper can do, a 12 gauge aluminum has to do. If you think of 14104, that kind of shows some differences in terms of size of what each size of conductor can handle. Pardon me. And if you compare tables 1 and 2 to tables 3 and 4, there's also a difference in size and allowable ampacity between copper and aluminum. Now over to the next page, we have supporting of conductors. And this is going to get specific into especially vertical runs, and especially vertical runs of armored or sheathed cable, such as Tech 90, RA90, RC90, AC90, and ACWU90. And so the reason or the logic behind why we need to be so specific is if we look at this picture from your module, this is, obviously that's Tech 90 because it's labeled and that's RA90, but these metal armors on these cables are not attached to the cable insulation underneath. It's basically just pulled over, if you want to think of it that way. So if these were run vertically and we had this cable terminated, then over time, gravity is going to start to pull this armor down, which may add strain to wherever this is terminated, and it may rip this conductor out of the termination point, or the device, or wherever it's attached. And so there's specific rules if you're using armored cable for how it is supported when it's run vertically. So one way you can do it is you can just have bends, because then the weight will be on the outside jacket instead of on the termination point, which is probably okay. Saying it's okay here. Now we're going to jump down to 12,300. Talking about exposed wiring on exteriors of buildings and between buildings on the same premises, on the premises, same place, same area. Now, an important note and the difference between overhead and exposed wiring on so on and so forth is this is talking about wiring run on the exterior surfaces of buildings or between buildings on the same premises, which is basically the same thing as the title. But I mentioned that specific difference because when we talk about our neutral supported cables, I actually show that on the camera, our neutral supported cables, which are usually run overhead as an overhead service to our houses, that overhead service is not technically exposed wiring. It's a little different. It's run overhead. Now, it is exposed to the elements, but it's not exposed wiring on buildings. So you can't actually run neutral supported cable exposed on a building. You can only run it overhead. And you might be saying, but it's in the exposed wiring section. What do you mean you can't run it exposed? Well, if we go to our handy dandy table 19, here we are, table 19. I'm on page 484. I should say that probably slower so it's legible. And I look at neutral supported 75 and neutral supported 90. It could be dry, damp, wet. Okay, that's good because it's going to be outside. Consumer service. Yep, sweet, that's good. Control and instrumentation. Cool. 12,308. Outdoor overhead. But it can't be run exposed, which is what I was talking about. You can't run it concealed, raceways, cable trays, or direct burial either. And exposed to sunlight basically has to be, this is just saying it has to be rated. So it has to say, yeah, I'm okay with UV rated or UV rays hitting me as a cable. I'm cool with that. You can't run it in plenums. I mean, sure, yeah, if you can't run it, exposed or attached to buildings, probably not good to run it inside of ductwork or plenums. But it can be outdoor overhead. And so your module lays out basically what all that means. So this would be your neutral supported cable, and it's coming in, it's overhead, it's attached to this building in some way. Cool. And then it's spliced onto these conductors, which are then run as exposed wiring on a building. And then it comes over to your rain head and it comes down. We remember all that from our talking about service requirements. And so that's sort of what it means. It's not run as exposed wiring on a building. It's run overhead and then tapped off. And now it's exposed wiring on a building. But if you remember from, or if you saw it in section 6, if this was a service, this door would need to be a meter from these cables. We always have to remember other sections of the code book for basically all electrical installations. Because if this was a service, let's jump back to section 6. Here I am, 6112. Exposed conductors or cables that are not higher than windows, doors, and porches, so have a clearance of not less than 1 meter from windows, doors, or porches. It has to be a meter away from that door. We don't want someone, walking into this building and high-fiving these service conductors, just slapping them, hey, what's up? Giving them a high five, getting their day started right, getting themselves charged up for the day. No, we don't want that. So it has to be, we need to have a meter clearance. And then it's got these other requirements for basically running exposed wiring on buildings. But I wanted to talk about the difference between overhead and exposed because they both are sort of in that 12,300 section. So I touched on flexible cables, which would be 12,400. So we're going to jump over to 12,500, which is non-metallic sheathed cable, such as this type of cable. This is NMD 90. This is a 2-conductor. You may have called this Lumex, or this brand name, if you can see it on the camera there, is actually Romex. And so let's just look at this jacket for a second, because it has a bunch of information that might make more sense now that we're progressing through the code book. And let's put a blank piece of paper behind there so the code book doesn't mess with the camera so much. Anyway, so it's got this number. Sure, it's CSA, which is good. It is a 14 gauge. It is a conductor 2 type wire. So it's a 14 gauge 2 conductor. It's got whatever this means. NMD 90, nylon, Romex, brand Simple. Cool. It's good for minus 25 degrees Celsius, up to 300 volts, and it's FT1. So if you remember back to the beginning, talk about those plenums and the fire spread and so on and so forth, and it's got a patent here as well. Looks like it has a date of manufacture. And if you remember from grounding and bonding, this is our bond wire. So this is a 2-conductor, and we're not talking about the bond when we talk about the conductors and the cables. And the jacket there, or the cable insulation, was talking about 300 volts, and that makes a lot of sense. If we look at 12502, which is the maximum voltage, shall not exceed 300 volts between any 2 conductors. Okay, so that's probably why they have it rated for 300 volts. If you've worked commercial, RW90 is usually 600 volt rated. You can get 1000 volt rated RW90 or R90 as well. And if we look at the scope, this is talking about NMD90. Cool, set it right on the wire. Also NMWU. Maybe NMW might qualify as well. That's in table 19. There's an NMW, in table 19. And we're not to install this NMD, this non-metallic sheathed cable, in non-combustible structures unless it's acceptable. It's for combustible construction. So a commercial building that's made of concrete and metal studs would be non-combustible. So NMD you're probably not going to see a non-metallic sheathed cable in a commercial building, or at least you shouldn't. I wouldn't say I haven't seen it, but you shouldn't see it. And then we get into 12506, the methods of installing non-metallic sheathed cable. And it's going to be running continuous lengths between outlet boxes, which are essentially receptacle boxes, or boxes where you intend to put a receptacle. So a box that's about a foot high in a house, or, on the kitchen counter, for examples. Those are probably outlet boxes. They're intended to have a receptacle go into them. Also, octagon boxes where you're going to put a light. That's an outlet box. Junction boxes and panel boxes as a loop system, and the joints, splices, and tabs shall be made in the boxes. So you can't just run it up to the attic, do a splice, and carry on with the other end of the cable. You have to do it in a box. You have to protect that splice or that tap or that joint. It has this rule for proximity to heating sources, and basically we already don't want heat, excessive heat, on our conductors, but this jacket is like a nylon. It's kind of a type of plastic, which means if it's by excessive heat, it could possibly melt, which would then, let that excessive heat get at these conductors underneath, which we don't want heat getting to. So there's these rules, and then there's these rules for distance from certain sources of heat, and then there's a specific barrier that you can put between the NMD or your non-metallic sheath cable, I should say. You could run other NM cables, but basically there's also this building code specific type of protection where you can put between the cable, and there's all these ways you can get around it if you have to, but in general we just run NMD 90 not with things that are going to make a lot of heat. And then we also have, for methods of installation, you have to staple it flat. Okay, if you have it up on edge and then you're hammering that staple on, it might squish those wires together and damage the insulation inside, cause a short. What's the point of installing a cable if you're just going to damage it? There's no point. So you have to make it flat. You don't install it, you don't have it like this and then you staple it like that. You lay it out nice and flat. You be nice to the wire. You just did all that effort to put it in. You're going to staple it. Basically, if my fingers are the staple, you're going to staple it flat like that. And hopefully your journey person told you to do that. If not, Codebook's got you. Says, yeah, go ahead and do that. Now, in terms of supporting this cable as we run it, as we, put in multiple staples to keep this cable upright and installed, your module has a pretty much perfect picture for exactly how to do that. But essentially, if you need to do a calculation for how many staples, they will give you a length. You will take off 300 meters from each outlet box, which there's basically always two outlet boxes, right? We're not going from an outlet box to nothing, but make sure it tells you there's two outlet boxes. Perhaps they're going to an outlet box and then out to another one, and they want to know for the full run how many staples. Okay, cool. So for each outlet box, you're going to take your total distance and subtract 300 millimeters for each outlet box. Then you're going to divide the remainder by 1.5 meters, and then you're going to round down. So if it gave you, let's say you do all that and it gives you 4.9 staples, you're going to round down, because you could also draw it out if that helps, but the math is kind of a simpler way to think about it and to count. And the reason we round down is because we just need to have basically not more than 1.5 meters between staples. So that's just kind of how we count staples for to see how many staples we need to meet code. And of course, you could always do more if you wanted. If it seems like the cable's just slacking, just slam another staple in there. There's no reason, or there's nothing against going above code. Now, you can't put NMD 90 in cement. That jacket can't really handle that. There's rules for non-concealed. There's, for example, this one's talking about running boards. And if you have them behind, just don't put them behind running boards, basically. But if you're going to, those are some of the rules. But when it's concealed, which is normally how we run it for new construction, when you're running your NMD down a stud and there's going to be drywall over after you're done, which is often the case with houses where we live, at least, that's going to be in a concealed installation, right? The drywall is going to cover that. It's now concealed behind the drywall and it's on the stud. And you run it through the studs, right? You drill a hole in the stud and you run it through that stud. It has to be 32 millimeters from the edge or the front edge of that stud, because as the drywallers come and start putting their screws into the stud, we don't want their screws to hit our wire. Because once again, what would be the point of installing it if it was just going to get damaged? It even says, more specifically, when it's run along studs, joists, similar members, the cable shall be at least 32 millimeters from the edge of its members. So the front edge of that stud is what that means. That can be covered by drywall or a similar material. And if you don't do that, then you need to put in a protection plate. And those protection plates usually have a CSA stamp on it. And we use those specific protection plates because they're manufactured as a corrosion-resistant ferrous metal, and they're not less than 1.3 millimeters thick, securely. They're designed to protect the cable should the hole be too close to the front of the stud, or more importantly, if the cable's too close to the front of the stud because of where the hole is. And if it's behind a baseboard, you have to protect it from the nails that are going to hold that baseboard on the wall. And we can use non-metallic tubing or conduit to basically used as a sleeve to protect the NMD if it's going to be exposed. It's going to pass through a floor, perhaps. And we can fish, right? If you're going to fish the wire down the wall, well, as long as there's no metal stuff that could cut it, you can fish it down the wall and you don't have to secure it, because what would be the point of fishing it down the wall if you're just going to pull the wall off anyways and secure it? There'd be no point in fishing it. You just pull the wall off first, run your cable, staple it, and then you would, go about your merry day. The provision for bonding is basically just going to take you to section 10, but the bonding wire is integral to the cable, we say. When they manufactured this cable and they put this cable insulation over these conductors, they put this bond in there. So sweet, that comes with a bond. That's kind of easy. And then we go on to armored cable. You may have called it BX in the field. It has that kind of interlocking armor around the conductors. And now we can install armored cable, or now that we're installing armored cable, I should say, we can install it in either combustible or non-combustible buildings. So if you've worked on commercial projects, you've probably dealt with BX, or AC90 is the code appropriate term. So turning the page, still on 12602, subrule 2 is talking about armored cable shall be of the type listed in table 19, suitable for direct burial, and table 19 has some other exceptions, and not exceptions, but what's allowed when you're using armored cable. And then down to 12610, when we're terminating armored cable, and basically when we sort of strip back or remove the metal protection, the metal armor, and we expose the conductors, so we can strip the conductor insulation and terminate them and stuff, we need to make sure that metal armor is not going to cause a short or a problem on the conductors. I mean, there's not much point in using an armored cable and protecting those conductors all the way just to have the armor itself damage them at the end and make it all for naught. So have you ever seen that little plastic bag of anti-shorts stapled to a reel of BX? That's what those are for. When you put the BX or AC90 into a connector, and that connector clamps down, and it clamps down and grabs the cable. We use anti-shorts to make sure that as the connector grabs the cable, that grabbing doesn't make the armor cut the wire and cause a short. You may use a type of armored cable, such as, this looks like some tech maybe. Regardless of what we're calling this, this picture is a perfect example of if you have this type of insulation on all the wires under the armored cable, or under the armor, this metal armor, and you can see it has all these burrs and it could possibly cut something, then you need 5 millimeters exposed to protect the conductors. So this cable basically has 3 sort of tiers of protection. It has this plastic sleeve for the conductors, it has this hard metal armor, and then around that armor it has another plastic sleeve. So if you have this type of cable, sure, you can use this inner jacket, you use 5 millimeters of it as an anti-short when you're terminating it. Now, if you have dealt with BX, you may have seen that paper that covers the conductors under the metal armor. And you might be wondering, hey, does that work as anti-short? Well, no. Basically, no. It says right here, I'm in Appendix B, page 583, the paper or plastic wrap around the cable core directly under the armor of an armored cable is not considered the inner jacket, referred to in item B. So that paper for AC90, the paper under the metal armor, does not count as an anti-short. And on to 12616, once again, when we have concealed armored cable, just because it's an armored cable doesn't mean we don't need to protect it, because screws can still go through that armor. So just in case, once again, we're not at least 32 millimeters from the nearest edge, we may have to put extra protection in case someone starts putting screws into that stud. And then the last one for armored cable, and the last one that I'll talk about for part 1 of section 12, when we're running the armored cable between boxes and fittings, we have pretty much the same strapping requirements as non-metallic sheath cable, 1.5 meters. And then from the box or the connector on the box, the strapping requirements or the support requirements could depend on trade sizes. So if you have a trade size conduit between 35 and 78, then your support requirements are 600 millimeters of every termination point. So every time it goes into a box and gets terminated or spliced, you can be 600 millimeters from that termination point if these are your trade sizes. Or if it's larger than trade size 78, it would just always be a minimum of 900 millimeters from the termination point. And once again, if you have it going through a stud and basically it's sitting in a hole on that stud, it's supported. That does count as support. Now, once again, let's just see what these, if you're trying to conceptualize what it means by trade size conduit. Page 37 of the codebook has these metric designator. So when we talk about, we're just talking about 78 trade size conduit, that would be a 3-inch conduit, tubing, fitting, etc. So if you're ever wondering and you need to imagine that, that's page 37. And that'll be the end of part 1.